Before we begin section 5.3, which is the fundamental theorem of calculus, I want you guys to take a second to look at the general antiderivatives handouts that you guys have gotten from me. And these are general rules that we should know. This is going backwards from taking a derivative. And so to integrate this integral symbol of x to the n dx, instead of subtracting 1 from the exponent, is what we did for the power rule for derivatives, we're going to add 1. And instead of multiplying by that value out in front, we're going to divide by it. Likewise, the rest of these, take some time to study these and know these. Definitely something that you need to have memorized. It's going to be very helpful to know these for this class and then also for Calculus 2 and Calculus 3. The fundamental theorem of calculus is key since it connects the two branches of calculus, differential calculus and integral calculus. The first part of the fundamental theorem of calculus deals with the function defined below. G of x is equal to the integral from a to x of f of x dx, where f is a continuous function on a to b and x varies between a and b. If f is a positive function, then g of x can be interpreted as the area under the graph of f from a to x. The fundamental theorem of calculus part 1. If f is continuous on a, b, then the function g is defined by g is equal to the integral from a to x of f of t dt, where x is a value between a and b. I want you guys to realize a is a number and x is a variable. And this is continuous on the same interval and differentiable on the interval also, not including endpoints. And the derivative of g is equal to f of x. So another way to look at this, again, since this is a higher level math class, thinking of things a little differently, the derivative of that integral from a to x of f of t dt is just equal to f of x. So we have an example down here with the picture. This one says, let f of x be the graph below defined by g of x is equal to the integral from negative 1 to x of f of t dt. Evaluate each of the following. So first of all, we're dealing with an integral that's talking about the area underneath a curve, but I want you guys to remember that the area above the x is going to be a positive area, and the area below is going to be a negative area. So we're going to have the first one is, this is our x value. So we're going to have the integral. So g of 0 is equal to the integral from negative 1 to x, and x this time is 0, of f of t dt. And remember, area is talking about, our integrals are talking about the area. And so if I go from negative 1 to 0, that area in here that we have is 2 boxes, however they are underneath the x-axis, so that means that this is going to be equal to negative 2. The next value that we have is going to be negative 1 to 2 of f of t dt, which is equal to, and so now we're going to go from negative 1 to 2, so I'm also going to be adding in this area here. So we have negative 2, which is what we have from negative 1 to 0, plus going from 0 to 2, that works out to being 1 whole and 2 halves, which is also equal to negative 2. So this is a total area of negative 4. G of 6 is going to be negative 1 to positive 6 of f of t dt. And so if we think about this, you guys can think about it as going from negative 1 to 2 of f of t dt plus the integral from 2 to 6 of f of t dt. And since we already know the first integral from part, or the one right before it, that is going to be negative 4 plus, and then going from 2 to 6 is this area in here, which is now above your x-axis, which is going to be positive. And that area, it's a triangle, is 1/2 base times height, which is going to be 1/2 4 times 4, or half of 16, which is 8. So this total area would be 4. The next one that we have is going to be the integral from negative 1 to negative 4 of f of t dt. And that first value should always be your smaller value. That's your lower limit. And since these are backwards, we're able to flip these. And rewrite this as -4 to 1, but you have to put a negative sign out in front since we did switch those limits of integration. And this is going to be of f of t dt. And so going from -4 to +1, we have this area in here. And that area is equal to -6, but be careful because we did have a negative out in front here. And so this is equal to +6. And then the last one we have is from -1 to -1 of f of t dt. There's no area defined there. Your limits of integration are identical. They're the same like we've seen be in previous sections. That's just defined as 0. So moving on. The next example that we have says find the derivative of g of x, which is equal to the integral from 4 to x of the square root of 1 plus t cubed dt, and evaluate g prime of 2. So there's two things it wants us to do. First of all, I want you guys to realize that our function here is continuous on the domain. So from 4 on, it's going to be continuous. The next thing that we have is going to be finding out the derivative of g of x, which is going to be the derivative of the integral from 4 to x of the square root of 1 plus t cubed dt. And this is just going to be equal to, so g prime of x, the derivative of g is g prime of x, if you guys want to write it that way, is just going to be equal to the square root of 1 plus x cubed. And then it's also asking for us to find g prime of 2, which is equal to the square root of 1 plus 2 cubed, which is equal to the square root of 9, or just 3. The next example that we have says find the derivative of the integral from 4 to x of sine of t squared dt. So first of all, our function here is continuous on the domain. For sine, it's all real numbers. And so we're asking to find the derivative of this integral. And using that fundamental theorem of calculus, we have this is just going to be sine of x squared. And that's it. The next example we will look at together. I want you guys to realize that those limits of integration are written with the variable first and the number second. So think about how that might be handled. The next part that we have is the fundamental theorem of calculus, part 1, but using the chain rule. And this could have been extended onto the first page and been presented in that way. So first of all, we have the derivative of the integral from a to g of x. A is still a number, but this time you'll notice instead of x as your upper limit of integration, it's written as a function, so g of x. So it's not just a variable. And of f of t dt is equal to, if you notice the first thing you have is f of g of x, substituting that value, times the derivative of g of x, where a is a real number. So we have evaluate the derivative of the integral from -2 to cosine of x, sine of t dt. So again, sine is continuous, so we can go ahead and use that fundamental theorem of calculus. And this is now not, up here, our upper limit of integration is not just a variable, this is a function. So this is going to be written as sine. And instead of t, we're going to substitute in that upper limit of integration, which is cosine of x, times the derivative of that upper limit of integration, which is negative sine of x. You can definitely clean it up, not too much, but if you wanted to rewrite it, you definitely could. The next one we will save and do that one together, but look at the limits of integration and realize none of those are numbers. One's a variable and one is a function, so kind of think about how you would handle that. Recall that capital F prime of x is equal to f of x. The indefinite integral of f of x is given by, and this is something that we need to know here, so give this a big old star. This is coming from section 4.9. So if you notice, your integral has no numbers on it and no variables and no x's or anything along those lines. And so when you integrate it, you have to add a plus c. We will go through a derivation of that and why that's important later on. Also, recall that the integrations techniques used in section 4.9, that was that handout that you guys saw. There's a few of them on here listed. First one is the power rule for integrals. That's the first one that's listed on that handout. And so you're going to add a power, add 1 to your power, and divide by that same thing plus c, where n is a real number. Sum and difference rule says that if you take the integral of a bunch of terms, you're able to integrate each term individually. Constant multiple rule, if you have a constant, you can pull that out in front of your integral. The general antiderivative of 1 over x is equal to ln of the absolute value of x plus c. Fundamental theorem of calculus part 2. So definitely important. Assume that f of x is continuous on the integral from a to b, and let f prime of x equal f of x on ab. Then the integral from a to b of f of x dx is equal to the integrating each of those f of b minus f of a. I want you guys to realize it's the upper limit of integration minus the lower limit of integration. Informally, the fundamental theorem of calculus part 2 says that we can evaluate a definite integral by solving for the antiderivative f of x, substituting the limits of integration b and then a into f of x, and then subtracting. Notice that there is no constant when evaluating a definite integral. So we'll talk about the differences too. We have a definite and indefinite integrals. So the example on here says evaluate the integral from 1 to 3 of x squared dx. And this has values on it, so this is a definite integral. And so we're going to go ahead and use that power rule with this. And using the power rule with this, we get adding 1 to our exponent. That's going to become x to the third. And then we divide by 3. You can always check to make sure this works by taking the derivative of it, since now we're pros at taking a derivative. And if you were to take a derivative, you would have had 3x squared divided by 3, which would have worked out to be just x squared. We do not put a plus c because taking the derivative of a constant, it is gone. We do not need it. But we are going to evaluate this. And let's say you forget and you add a plus c. And we'll see that we don't need it. But we're going to evaluate this from x equals 1 to x equals 3. So you always substitute in from the fundamental theorem of calculus part 2, the upper limit of integration first. So we have 3 cubed over 3 plus c minus, and be careful with parentheses, the negative is very important in there and needs to be distributed to terms. Substituting in 1, we have 1 cubed over 3 plus c. And now you will notice why we don't need the c in there, because when we go ahead and simplify this, you guys will realize we have 27 over 3 plus c minus 1 over 3 minus c. And with these c values, that just equals 0. They cancel each other out. And then we have 27 over 3 minus 1/3 is 26 over 3. I will leave it like this. So what you guys just found was the area under the parabola x squared from 1 to 3. And it's not an approximation, this is exact. The exact area is 26 divided by 3. So looking at the next one that we have the integral from 0 to pi over 4 of secant squared of x dx. And if you go back and you look at your handout for the antiderivatives, or think about the derivative formula, we have this is equal to tangent of x. And I'm not going to put the plus c in anymore. Hopefully you guys can see that that cancels out whenever you have a definite integral. And this is going to be going from x equals 0 to pi over 4. So evaluating tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is just 1. Tangent of 0 is 0. So this works out to just being 1. So the area under the graph secant squared of x between 0 and pi over 4 is equal to just 1. The next problem that we have for C is going to be the integral of, and we're able to take the integral of each of these terms one by one. I'm going to go ahead and rewrite this as the integral from 1 to 4 of 3x to the 1/2 plus 2x. You should have parentheses around the whole entire part that you are integrating. That integrand should have parentheses around it. And then you definitely need a dx. That's the width of that rectangle. So if you miss the dx, that's technically wrong. You should get no points. So going through with this, we're going to go ahead and that constant value you can think of as moving out in front. And that's a power x to the 1/2. And I'm going to add 1 to it. So if I add 1 to it, I get x to the 3/2. And I'm going to divide by that same value, 3/2. Instead of dividing by it, you can also think of it as multiplying by the reciprocal. Then we have plus 2 times, and then it's going to be adding 1 to that exponent. We get x squared all over 2. And this is going to get all evaluated from x equals 1 to 4. I'm going to go ahead and clean this up just a tad, and I'm going to look at that first part with fractions. So this is the same as multiplying by 2/3 to the bottom and to the top. And you'll notice your 3's cancel there also. So we're left over with 2x to the 3/2. And if you want to rewrite it as roots, you can. I'll leave it for right now. Your 2's also simplify here. So plus x squared, evaluated from x equals 1 to 4. So from here we plug in our upper limit of integration, which is going to be 4. And then we're going to subtract, substituting in 1. So we have 2 times 1 to the 3/2 plus 1 squared. So we end up with, first part should work out to being 32 minus 3, so 29.